The discovery of the cosmic microwave background, or CMB, was a revolutionary leap in cosmology. In every direction we look, if we peer far enough into the cosmos, we can directly see the glow of the hot early universe, the light from the Big Bang itself. Detecting the CMB was often hailed as a triumph of the Big Bang theory, which continued to pass observational tests with flying colors over subsequent years. But the CMB ultimately ended up causing astronomers to rewrite cosmic history completely. In place of a singularity, our modern picture of the early universe now includes a period of unimaginably rapid expansion in the first tiny fraction of a second, cosmic inflation. There's a popular story about the Big Bang that you've probably heard before. The universe began as a singularity, a point of infinite density and zero size that appeared from nothing. That singularity contained all of space and time, and then it expanded, and everything in the universe came from that single point. But there are problems with that story. For one thing, in cosmology, when we talk about singularities, unless we're getting into something really weird and probably impossible, we're talking about infinite density, but not infinitesimal size. A singularity can be extended across all of space. In most circumstances, you should think of a singularity as a phenomenon of time, not a specific place. The Big Bang singularity could be in the universe's past, but not in any particular place and never in a single point. As it turns out, though, even an infinitely large singularity doesn't work well with the cosmic microwave background. The CMB is just too perfect. The CMB light is incredibly uniform. If it really does come from the glow of the primordial plasma, that means that the plasma was about the same temperature everywhere, to just 1 part in 100,000. But in the standard Big Bang model, there's no reason that the primordial plasma billions of light years apart on opposite sides of the sky should ever have been the same temperature. Normally, for two things to come to the same temperature, they have to be in contact for a while. Like how if you leave a coffee cup in a room for long enough, eventually the coffee and the air will be room temperature. But two parts of the sky in opposite directions were never in contact. They were always, from the beginning, too far apart for light beams or any other kind of information to pass between them. In fact, the light coming from them is meeting for the first time right here, right now. So how did 2 points outside each other's observable universe agree to be exactly the same temperature? This is called the horizon problem, because different parts of the sky seem to have somehow communicated despite being outside each other's cosmic horizons. The most widely accepted solution to this is to insert a period of extremely rapid expansion called cosmic inflation in the first tiny fraction of a second of the cosmos. Inflation fits between whatever the beginning was, possibly a singularity, and the hot Big Bang, when the universe was hot and dense. During inflation, space was expanding quickly enough to take a tiny, tiny region of space that, in those first moments, had already become uniform, and blow it up by more than 26 orders of magnitude, making it larger than our entire observable universe. All within a billionth of a trillionth of a trillionth of a second. Then, the energy field causing inflation decayed, filling the cosmos with radiation, and the expansion proceeded at a more leisurely pace. This might be hard to picture, so let's try a picture. In the original Big Bang scenario, we can imagine this is a view of the part of space that will eventually expand to become our entire observable universe. It has lots of different colors because all those little dots, though close together, are nonetheless outside each other's cosmic horizons. Now, if this bit of space expands as the universe expands, the sky should be a complicated mess. In the inflationary picture, the expansion in the early universe is much more extreme. Now, to account for so much expansion, instead of blowing up our original multicolored region of the painting, the part we're enlarging has to be an incredibly tiny speck, smaller than a pixel. So it's not surprising that the final picture is all the same color.
I love inflation. It's a very nice story where everything came into being out of quantum fluctuations and kind of nothing, like vacuum states. So it connects quantum mechanics to all the larger scale structure, everything we see in the universe today. But at the same time, it's a story that we cannot quite prove very well. So that's why I like to also look into other theoretical conjectures, possibilities, stories. At the same time, if some of them work out, then it might be that we don't even need inflation to begin with to explain the current observations.
Inflation solves a few other problems and makes some predictions that have matched the data so far. But it's still not proven. We still don't have a solid theory for what started inflation or why it stopped. And cosmologists are still searching for an extremely subtle quirk of the light of the CMB that could be a smoking gun for inflation's violent distortion of space. But assuming it's correct, one of its coolest aspects is the idea that the density variations in today's large-scale universe, traced by galaxy clusters and giant voids, all arose from infinitesimal quantum fluctuations in the energy field that drove the inflationary expansion. If cosmic inflation really did blow up the early universe, then quantum uncertainty is, literally, written into the stars.